Hey everybody, thanks for coming back. I appreciate you being here. So I did not receive a question. I don't know if either of you have a question for internal combustion engines, but I can just talk around a little bit how we go about solving them. And then I think hopefully that won't take the whole time. And then if you have other questions, whether they're about internal combustion engines or some other cycle or something, then we can just do those here too, right? So we can use this a little bit to talk about internal combustion engines, but also to talk about just the exam in general too. So internal combustion engines, right? For these, right, again, we got three big questions, right? The first question is how do we characterize the system, right? So these are going to be heat engines. So they're going to be net power divided by heat in, right? Now here, you can put dots over these, but because the answer to the next question, right, open versus closed, because these cycles are a series of closed systems, if we're just using the first law, then we can, the first law will only give us Q's and W's, not W dots and Q dots, right? And then the third question is what's the fluid? And it's an ideal gas. And because it's an ideal gas, we want to be watching out for processes where delta S is equal to 0, right? So the thing about these particular internal combustion engines is we're going to assume everything is ideal. Right? So in this case, when delta S is equal to 0, that will also be when Q is equal to 0. So anytime that there is no heat transfer, then you're going to be able to use an isentropic relationship. Now, to me, right, and it's not necessarily 100% true, right, but I think the way I think about it, the way I try to, right, to look for these delta S equal to 0 terms, it's when this Q is equal to 0. And that's definitely true here when everything is ideal, right? So let's look at Otto cycles and diesel cycles. I hope I spelled that right. So they're kind of similar, right? The difference is the assumption we'll make when we add heat, right? So first we start down here at state 1. We go through a compression stroke from state 1 to state 2, right? So the volume is getting smaller and the pressure is getting bigger. So this is our piston head is coming up so that the volume inside our system is getting smaller, but because it's the same amount of air, because they're closed systems, then it's, the pressure's going up. Now this is what makes an Otto cycle an Otto cycle, is that here, as we're adding heat, so this is power is going in. This is our compression stroke. Here we're going to add heat. And what makes an Otto cycle an Otto cycle is this happens at constant volume. Now, as we go down here to state 4, in state 4, this is our power stroke. This is where we're developing power, right? This is the whole reason that we're running the engine, right? So we can get power out, and then we're rejecting heat. A diesel cycle is very similar, right? The only difference is the assumption that we make when we're adding heat. So we start at state 1, we go through this compression cycle or compression stroke to get to state 2. But now when we add heat, we do it at constant pressure, right? And we'll see how that makes a difference here. Oops, this is 3 up here, and this is 4 down here, right? And we go like this, right? And we're moving around the cycle like this. So here there's still work coming in, work going out. We're still rejecting heat over here. But because this now is a constant pressure process, there is some work here, right? Work is the integral of P dV, which is equal to pressure, because pressure is constant, comes out, times delta V, right? Or maybe we could say pressure times the mass times the change in the specific volume. So what happens here, because the volume is expanding, we're producing some power as we're adding heat. So this is the difference between the Otto cycle and the diesel cycle. So diesel cycle is a little bit harder than the Otto cycle.
I have a quick question.
Yep.
So if the same amount of heat is added to both an Otto cycle and a diesel cycle, the diesel cycle would produce more work, right?
I think you'd have to probably do the analysis because
Okay.
it maybe depends on. I'm not exactly sure, right? Because you'd have to know what's going on. But I mean, typically diesel engines are used to generate more power, so it wouldn't be surprising to me if
Okay.
that's true. But I think you'd have to look to see what's going on at all the other states. But
Right.
your intuition to me seems to be reasonable.
So if that is true, then why would an Otto cycle, wouldn't a diesel cycle always be used over an Otto cycle?
If you were trying to generate more power, yes. So Otto cycles typically have better efficiency at lower powers, right? So you think about like a spark ignition engine is an Otto cycle, right? So if you have a Corolla and you're driving back and forth to work, then you have an Otto cycle because it tends to be more fuel efficient at low power requirements. But if you're driving a semi down the road, right, then you have a higher power requirement, and a diesel engine tends to be more efficient at higher power requirements.
So then,
At least that's my understanding.
okay, so if the same amount of heat is added and the efficiency of the Otto cycle is higher than the diesel cycle, then I guess the diesel cycle wouldn't produce more work if the same amount of heat is added.
I think it depends on your operating condition.
Okay.
Like so many things in engineering, there's no like one size fits all answer, right?
Okay.
So we always have to consider what's the application we're trying to do, and then what's the tool that gives us. I hesitate to say the best answer, right? But at least at first a satisfactory answer, and then we can sort of look at it and how to tweak it.
Okay.
So I think there's no, which is again sort of comes back to this idea of like, if it's the same amount of heat, will it produce more work? And I think it probably depends on where you are in the operating curve.
Okay. All right. Okay, thank you.
Well, and that's a really good question though, because you can tell because I don't exactly know what the answer is, but I think that's true. Right. So what would we do, right? So if we were trying to, like, let's say on an exam, you got first like an Otto cycle type question, and it says, what's the thermal efficiency, right? So here you want to find the net work, right? This is going to be, again, we're just going to sum all the places we're doing work, but some of them are going to be positive where we're producing work, and some of them are going to be negative, right? So in an Otto cycle, there's two processes where we're doing work, right? So we'd use the first law, and it would tell us that delta E is equal to Q minus W. We would assume that there's no kinetic energy change, no potential energy change, or at least that they're small enough that we can neglect it. So this is going to be M times delta little u is equal to Q minus W. That's true for all four processes. But now when I'm talking about the work processes, so here I would be going from 1 to 2 and from 3 to 4, Q is equal to 0, right? And then also from 2 to 3 and 4 to 1, W, oops, not W dot, but W is equal to 0. So then the first law tells me if I'm trying to do net work, this is going to be the mass, which is constant, so I can factor that out from all of them. Now this is delta U, right? So it's different because it's a closed system. So this is going to be U1 minus U2. And then we're going to add our other work process, which is from 3 to 4, minus U4. Right? That's going to be our work, our net work. Right? Our heat in, we look at our system, and where do we add heat? We add it between state 2 and 3. So this is going to be the mass times, between state 2 and 3, we're going to cancel out the work term. So this is going to be Q is equal to U2, no, it's U3 is the end point minus U2. So then if we want our thermal efficiency, it's going to be M times U1 minus U2 plus U3 minus U4 divided by M times U3 minus U2. And those masses are going to cancel out. So this is for the Otto cycle. It's a little bit trickier for the diesel cycle. For the diesel cycle, what stays the same, right? So for the diesel cycle, it's this process here that's different, right? The rest, all the other three are the same. So here, right, so the work for the diesel cycle, well, why don't I just do it, right? So for the diesel cycle, if I'm trying to find the net work, right, first I have the net work from that first process, right? So here I'm going to say, right, so this is going to be, I need the work from state 1 to state 2, plus there's work from state 2 to state 3, plus there's work from state 3 to state 4, right? So because there's this part here, the net work is different, right? But these other terms are the same as in Otto. So this is going to be, M times, this is U1 minus U2. Now we're going to have plus, this is going to be W23 over M, right? All I did was factor that out. Plus, from 3 to 4, this is going to be U3 minus U4. Right? So the thing about the Otto or the diesel cycle is you're like, well, how is it that I go about finding this work from state 2 to state 3, right? So remember, right, our PV diagram, state 1, state 2, state 3, state 4, right? So it's this one. How do we find the work here, right? So from here, we remember that work from 2 to 3 is equal to the integral of P dV, right? So we know that the pressure here is constant, right? P2 is equal to P3. So here I'm just going to say P times the integral of dV from state 2 to state 3, which is equal to P times V3 minus V2. What I really want, though, is work divided by the mass. We'll pretend that's an M from state 2 to 3, right? So here, if I divide this by the mass, then I get P times little v3 minus little v2, right? So that's now specific volume instead of volume. So what do we do now, right? So we remember that P2, or that P, this constant pressure, this is P2 and it's P3. So I'm going to multiply this through, and I'm going to make it P3 when I multiply by V3 and P2 when I multiply by V2, right? So this is P3 V3 minus P2 V2. Now for me, if I mess this up, it's going to be here and I'm going to make a sign mistake. But I think if I trust the first law like I've been doing, I think I'll get it right. So let's see if I get it right. So this is going to be the mass times everything. Right now it's going to be U1 minus U2 plus P3 V3 minus P2 V2, right, plus U3 minus U4. Right now I have things separated by what the process is. Instead, I'm going to go through here and I'm going to, it's tricky because it's hard to use the mouse and the pen at the same time. I'm going to organize these by state number. So this is going to be the mass times U1. Right now I have a U2 and a P2 V2. So this is going to be minus U2 plus P2 V2 plus, so now this is, I'm good with these, right? Plus, now I have a plus U3 and a plus P3 V3. So this is plus U3 plus P3 V3. minus U4. But I remember that this is H2, right? Our definition of enthalpy is equal to U2 plus P2 V2, right? And this is H3 here, right? So now this is going to be M times U1 minus H2 plus H3 minus U4. Right, so that's my heat transfer term. Or my, sorry, not my heat transfer term, my network. This is almost the same as the network for the Otto cycle, but in the Otto cycle, they're all specific internal energies. What happens, sort of by happenstance, is as we go to diesel, right, here we have state 2 and state 3, which are on this horizontal line, this constant pressure line. So these 2 points, or these 2 states that are on the horizontal line, go from U's to H's, which is the first letter in horizontal, when I talk about my network term. How do I find heat in for diesel? Again, I'm going to use the first law. I've already assumed here, right, that delta KE is approximately equal to 0, which is approximately equal to delta PE. So my first law is going to be the mass times, when I'm adding heat, I'm going here from state 2 to state 3. There's heat coming in here. So this is going to be U3 minus U2 is equal to Q from 2 to 3, that's Q in, minus W 2 to 3. But what I really want here is an expression here for Q23. So I'm going to isolate for that. Q2 to 3 is going to be equal to W23 plus MU3 minus U2. We already found W23 was this, right? So we know that this is P3 V3 minus P2 V2. This is also times the mass, right? Because this was not actually W23, this was W23 over M, right? So to get W23, I have to multiply that by the mass, and then I get plus the mass times U3 minus U2. Again, I collect by the state number from 2, 3, right? So this is going to be U3. I guess I'm going to put Q over M because I already ran out of room. U3 plus P3 V3 minus U2 minus P2 V2. And this is going to be H3 minus H2. That's for diesel. If we went back and looked at the Otto equation, it's the same equation, but these 2 points that are on that horizontal line used to be U's and now they're H's. So here, if I go to, this was our, right? It used to be Q in was U3 minus U2, and now it's H3 minus H2, because those are the 2 points on our horizontal line. So now if we go to our thermal efficiency, this is going to be, the mass flow rates, or the masses are going to cancel out, but it's going to be U1 minus H2 plus H3 minus U4 divided by M times H3 minus H2. The masses are going to cancel out. I could do this also as, right? So this is H3 minus H4. So I can make this also 1, right? Because there's a H3 and a minus H2 over here, right? So I can make it 1 plus U1 minus U4 over H3 minus H2. If I wanted to. It's the same thing, right? And it doesn't really save you getting other information. I guess this way there's less things to put into my calculator. And like I've said many times, I'm pretty good at putting things into my calculator wrong, right? So that's how we get the equations. Does anybody have questions about how we get the equations for these states? Or for these processes? How do we fix the states? Right? This is why we ask what the fluid is. The fluid is an ideal gas, right? So then we're going to have to make a choice, right? So first, I guess it means we can always use the ideal gas law, right? So we can say that PV is equal to mRT. This is, I said that there were 3 ways to find the mass in the last couple classes that we've done. There's really a 4th way to find the mass, right? So if they ask you how much mass is in a, right before I think last class, well, that was a mass flow rate, so maybe I'm still correct. If you're ever trying to find a mass in an internal combustion engine question, that's basically saying use the first law on some state where you know PV and T. Right? So here you're going to have to go through, and you have to know what the gas is, right? Remember that R is equal to R bar, the universal gas constant, divided by the molar mass, which is different for every gas, or at least potentially different for every gas. I guess you could have multiple gases that have the same molar mass. You put that in there, and that's why you get the specific gas constant. Usually on an exam, I'm not going to make you look up the specific gas constant, but I'll probably give you the universal gas constant and the specific gas constant so you can demonstrate that you understand what's the right value to use. Just like I'll often give you CP and CV, right? So you can demonstrate. Although if this was a constant specific heat problem, for diesel, you have to use CP and CV, right? Because here, delta U is CV times T1 minus T4. And here, delta H is CP times H3 minus H2. Right, so you might have to use both, but I would probably give you both, even if it was an auto question. So you had the opportunity to demonstrate that you understand which one to use. Right, so we have to pick between constant specific heat and variable specific heat. So here, if it's constant specific heat, delta U is equal to CV times delta T. Delta H is equal to CP times delta T. If it's variable specific heat, delta U is just equal to delta U. Delta H is equal to delta H. We're going to fix these things on our equation, or on table 822. Maybe we'll know temperature. Or because this is a closed system, we might also know VR. Typically for these, I can say it now. I'll go up here. Sorry, I'm breaking my chain of thought here, but I just remembered. So there's volume ratios that are important, right? So in a diesel or in an auto cycle, there's only 2 volumes, right? There's the big volume and the little volume, right? So here we only have a compression ratio for auto, and that's going to be, it's always big over little. These volume ratios are always more than 1. So it's V1 over V2, V4 over V3, or basically some combination of V4 and V1 divided by some combination of V2 and V3, right? But here we have 3 volumes, right? So here we do have still a compression ratio. So that's the ratio across the compression stroke. So this is still V1 divided by V2. But then we also have this cutoff ratio. And that tells us something about like what's the volume ratio when we stop adding heat, right? Or when the heat addition cuts off, I guess, right? Maybe that's where that word comes from. But it's still the bigger volume divided by the smaller volume, V2. So we'll often have volume ratios, or would like to find volume ratios, and that will be helpful for us as we move through this. Now, there is this trick, right? Let's see if I can do it on the fly here without... So here, because we can only use these isentropic relationships when we have only work, right? So for the diesel problems, you're probably going to have to find something like V4 over V3. The first thing we have to remember is that V4 is the same thing as V1. So this could be V1 divided by V3. And then we got to do this kind of sleight of hand where we multiply the right hand. Well, I guess we multiply both sides of the equation by 1, but it doesn't matter on the left-hand side, right? So here we're going to, but the 1 we multiply is going to be V2 divided by V2. So this is going to be V1 over V2 multiplied by V2 over V3. You can see here I didn't cheat. This math is still true because I could cancel out the V2s and I'd still have V1 over V3. The reason that I do this kind of weird thing is that V1 over V2, this is R, and V2 over V3 is 1 over RC, right? So V4 over V3 is R over RC. But don't just memorize this ratio, because you might end up writing down, when you're doing this thing, you might end up writing down V3 over V4 too, which is going to be RC over R. So if you're doing this, then try to take the time to do this, or look back at your notes. Don't get this flipped over. Right? You can always check your work too. If you just write this down, you can write down what RC is and what R is. Sorry, that was a bit of an aside, right? And the reason that those volume ratios are important is because, this is an internal, or this is a cycle that uses ideal gases. And Dr. Scherzer tells me that anytime we're using ideal gases, it's super important that we know which of the processes are isentropic, right? So here, right, because this is a closed system, I'm probably going to be using the expression. Here, let me just pull the equation sheet up because I want to make sure that I don't get it wrong. Right, this is going to be V over V is equal to VR over VR. But I don't, does anybody have the equation sheet open? It's okay if you don't, I'm sort of bringing it up here too. I never remember if it's, if it's 1 on top, is it then 1 on top on the right-hand side? So I always want to look it up because I don't want to do it wrong then here, and then you refer to the video instead of the equation sheet, and you find out that.
Yeah, so it's the 1 on top for both.
So it doesn't invert. So if this was, say, 1 over 2, then this would also be 1 over 2?
Yeah.
And then the other one, so this is variable specific heat, but if it's constant specific heat, this would be T1 over T2 is equal to, this would then be V over V to the K minus 1. Does this one invert, or is this one the same?
For that one, it's saying T2 over T1, and then it is inverted, is equal to V1 over V2.
Yeah, so here, so if we had this as 2 over 1, just to be consistent with the equation sheet, then this would be 1 over 2. Right, and we just have to make sure that we can only do that with an isentropic process. So this is why, right, in the diesel cycle, when you go from state 3 to state 4, this one is isentropic. So you might be trying to find, right? So you might say, oh, T4 over T3 is equal to V3 over V4 to the K minus 1. And you might say, oh, but I don't have V3 over V4, right? So here, then I would remember that this is the same as V3 over V1. And then I'm going to multiply by V2 over V2. So this is V3 over V2 times V2 over V1. And that's going to be equal to, this is, I think, RC over R. Right? And just like over here, we might do this. Maybe we fixed again, so if we were going to do from state 3 to 4 over here, we would say, let's say we've already fixed state 3, right? So if we've already fixed state 3, then we'd have, maybe I'd have V4 over V3, because I'm trying to find state 3, is equal to, this would be now V4 over V3. And V4 over V3 is going to be the opposite of this, right? It's going to be R, or the inverse, over RC, right? And then what would happen is we'd know these two things. We would have already fixed state 3, and then we go to table A22. We look up VR4. This should be VR4, I'm sorry. And then once we have VR4, right? Remember how that table looks like? So there's more stuff on this table, but it'll have temperature, it'll have specific internal energy, and it'll have VR on it. So like state 1 will probably have the temperature. We'll go through this way and we'll get U, and then we'll get VR. But in this case, for state 4, we would go the other way, right? So we'd use this relationship to get VR, and then we'd get U, and then we'd get T. So that's actually a lot like the Brayton cycle, right? It's just now we're using a different isentropic relationship because it's a closed system. Could we use PV is equal to MRT equation to find the mass flow rates, or mass only? So because it's not M dot, right? So the ideal gas law, right, or the ideal gas equation, whatever you want to call it, PV is equal to MRT. There is no mass flow rate inside an internal combustion engine, right? So here, this is going up and down, and the volume is constant, and the mass inside the volume is not constant, but the mass inside the volume is constant. So here you can solve for M. Could I use the ideal gas law to find a mass flow rate? I think I would have to divide both sides by delta T, and then take the limit as T approaches 0, right? And I get pressure times the volumetric flow rate is equal to a mass flow rate times RT. So this might be true, but if I had a volumetric flow rate, I would just do that the mass flow rate is equal to the area times the velocity over the specific volume, right? Let's see if these two equations agree. This is going to be exciting for maybe only me. P V dot over RT, right? And this is telling us that this is going to be V dot over the specific volume, right? So now what we see here is that, so what does P over RT mean, right? So now if we went to the ideal gas law, PV is equal to MRT, right? So then we want P over RT. So P divided by RT is equal to M over V, which is 1 over the specific volume. So these two things are the same. So this is equal to this. So you can use the ideal gas law to find a specific or to find a mass flow rate in an open system. But probably I would just use this expression here. But this expression, usually we just derive this from sort of an integral of the flow through a pipe. But you could get to the same place from the ideal gas law, it looks like. There's probably some, right, assumptions that we don't see in here, like we're assuming these properties are constant across like a cross section or something like that. So that's kind of at least generally what's going on with internal combustion engines. Does anybody have specific questions? We'll go first with internal combustion engines, but then we can take some time and just ask sort of general questions about the exam. So does anybody have questions about internal combustion engines? Okay, does anybody have questions about the exam or the content of the exam? So either like the mechanics of how we'll do the exam, or the content, just general thermal questions. And it's okay if you don't. I will stick around, but the other thing, so do people think, so I have office hours, regular scheduled office hours today at 2:00. I will keep those hours if people want to come. So I've had one person who said that they probably want to come to that. So I imagine that I will keep those hours if you'd like to come. But if you'd like to ask those questions now, we could try to go over them too. Okay, like I said, I'll stick around here, and if people want to ask questions, they're welcome to. But otherwise, good luck, everybody, and I can see you again for office hours today. But then otherwise, we're going to write the exam on Monday. I will, if you have an alternate start time, I'm planning to send you an email today just to confirm that the alternate start time from the second exam still works for you. But I was going to start, otherwise I was going to start, what did I say? I think we were going to start at the same time. Let's see what the announcement says on the course. 6:30. So if you have a conflict, if you have been writing at the kind of normal start time and you have a conflict with Monday at 6:30, I need to know today. But otherwise, that's what it's going to be set up for. Okay, if there's no other questions, that's good. But if you got questions, that's fine too.
All right, thank you, Professor.
See ya. Thank you.
I had a quick question. I remember that you had in one of the videos you were going over, I believe, a question that was like, I think it was an ideal pump where you had V is equal to the change in pressure, and you were trying to calculate for that. You said that, yeah, it was an ideal pump because I think you said the word water. You said that V was almost always 0.001 meters cubed over.
If it's water, it's you can look them up. Let's see if I can bring up some tables over here. Sorry, I'll let you finish your question just while I'm looking up the tables.
I was just mostly like, I just want to know why it's always almost 0.001 versus like looking through the table.
Well, it's kind of incompressible, right? So here's, let's do it in pressure because I think it's a little more, right? So remember, this is our saturated liquid, specific volume, right? But it's multiplied by 1,000. Right? So this is really always 1 over 1,000. So, 1 atmosphere is kind of here, right? So here it's 1.04. Right? So that's 1 atmosphere, right? So now here at 100 atmospheres, right? That's pretty high pressure. Right? It's not really atmospheres, it's bars, but it's almost the same thing, right? Then it gets to 1.45 divided by 1,000. Right, so I mean that's not nothing, right? It's 50% different, but I mean, it goes from, so it's between 0.9 and 1.1, or it's between 1 and 1.1, up until we get to 7 bar, right? So that's not terrible. It's always about 1 over 1,000. These pump terms, especially, they're also going to come into, but here if you get to 220 bar, well then it's 3, so it's not always 1. Right, but 1's a pretty good approximation if you're just going quick. Also, usually we're using that expression when we're trying to find pump power for a Rankine cycle, right? And it tends to be pretty low, right? So it's maybe 1 or 2% of the total. So even if you're off by 50%, it probably doesn't matter too much. But because we're just going to look up the specific volume, it's just VF of whatever the temperature is or the pressure. Doesn't take a lot to look that up. So I would still look it up. But if you get, something that's not close to 1 over 1,000 or even as high as 3 over 1,000, then that means you did something wrong. right? Density of water is always around 1,000. I guess not always, but usually around 1,000. So if you get that the density of water is like 20,000, then you did something wrong, right? And it's easy to mess up your, to do all the process right, but because of the units or whatever, because you read it off the table wrong here, and you forget to divide this by 1,000, it's easy to be off by like a factor of 1,000 or a factor of 10,000 or something, right? So it's more like just have a look at it to see it's around 1/1,000 as opposed to always use 1/1,000. But if I had no time on an exam and I was just trying to plug stuff in, I'd probably plug in 1/1,000. Does that kind of make sense?
Yeah.
So I guess there's some nuance, but it's always going to be around that number.
So like if we're like running out of time, if we just do that, then
yeah, if you're
like
running out of time
point.
too, my first suggestion would be get as much symbolic information as you can on the exam, because I think that if you're running out of time, that's your best bet to be demonstrating that you understand how to do stuff, as opposed to like doing an interpolation on your calculator, which I don't actually see. You just write down the number, probably. Right, but yeah, if you're rushing to get to the end and you start, estimating numbers, if you have to estimate the number for the specific volume, 1/1,000 is not a bad number to estimate. That's a pretty specific set of circumstances, but I guess, yeah.
I mean, if we interpolate, do we write down the entire, I guess, the work that we do?
Not at this point. That's fine. You don't have to. You can say that you're interpolating and then get it. And this is another thing, I guess, too, because the specific volume of the saturated liquid is not, it's a weak function of pressure, right? So I wouldn't interpolate between any of these rows. I would pick one. I might, I guess, if it was 85, I might take a number that looks about halfway in between here. But I mean, is there really a big difference between 1.3842 and 1.4178? Especially when I'm only going to put in 1.4 in my calculator in either case.
When would we actually other than when we are using H to find T, or let's see, or when we have X for quality, when would we interpolate?
Well, anytime you use the quality equation, you're interpolating.
Right. Other than that time, is there any other point to interpolate, or can we just take the closest number that is?
At this point, I'm less worried about, can you do the arithmetic of interpolation? So if you just want to, let's say you have a number here that's 253. If you just kind of tell me that, and you're trying to find H, and you just say, I took a number that's closer to this number than this, so I just picked 3,000 or 3,005. I'm probably not going to get too worked up about that. I think that the thing you're trying to demonstrate on this exam is, do you know how to do cycle analysis? So I would spend your time and your resources doing the cycle analysis over doing the linear interpolation.
Okay, then what would be, so if that's the case, what other things would we that we usually do would you not need to
Yeah, I mean, part of this is you got to use judgment about what's important and what's not important, right? I'm very hesitant to say don't ever do this on an exam, because invariably at some point in the future, even if it's not in this class, because I'll post this video on YouTube, somebody will say, well, you didn't, you told me I didn't have to do that. So I think you've got to think about the spirit of the question, right? And remember that your job as a student on an exam is to try to demonstrate your understanding of how to do stuff, right? So when you're doing cycle analysis, really the stuff that you're trying to demonstrate that you know how to do is answer those three big questions, use the first law and the second law, and maybe conservation of mass to get symbolic solutions, and then use your information about what the fluid is to try to fix the state. In general, I'm not that concerned with uncertainty or error that's associated with getting that number, provided you're following the right process, right? So again, I'm grading the process. So to me, the process is, oh, I found that it was water. I went to table A4 and I got a number here. Now, let's say the number was actually 160, but I just quickly thought it was 260 and I took a number in between here. You're probably going to lose a point for that, right? But you're not going to lose like 10% of your grade because you still demonstrated that you knew what you were doing, right? You just made a mistake because you're human, right? Everybody's human. We all make mistakes like that, right? But if you, if you didn't solve the first law and didn't get the equation and then didn't realize that you had to find H, then obviously you've demonstrated less understanding than somebody that, picks a number off the table well. Does that kind of make sense? I know it's not super comforting, probably.
That makes sense. Thank you.
Yeah. Right? It's always a little bit tricky. And then, some of it too is that the grading is, sometimes the question is either easier or harder than maybe what I think it's going to be, right? So the things that I look for when I'm particularly grading might be different than the things I thought I was going to look for, right? So if I get a question and everybody does very poorly on it, right? Then my grading kind of scales to be more about like how much of the big picture process did they get, right? Whereas if there's a problem where everybody does really well, then it's a little bit less of that, right? And again, I know it's a smaller class, so it's a little harder to do that, right? To get the right sense of how the problem is. But I think we saw that a little bit in exam 2, particularly because the question was a little hard to understand, right? So that problem, we graded more based on the process, right? The big picture process. I think just try your best, trust this process, use the first law, right? This is the one thing I can tell you, one thing absolutely don't skip. Do not skip writing down the first law or the second law and writing down your assumptions. Because to me, that's the whole game, right? That's like not the whole game, but that's the majority of what to me this class is about, right? Maybe on the first day I told you that, in thermodynamics, it's one of the first classes where we get to really do what I think is engineering, which is where you're trying to find a good solution with an imperfect understanding of the universe, right? And what that means, hopefully now, when you look at that is, that means I know what the right equations are, but I don't have all the information. So I got to kind of use my understanding of the problem to see, well, what's the stuff that's the most important, right? What's the stuff that's going to drive the answer that I get, right? And as we've said, that steps you more towards the cartoon and less towards the reality. But sometimes the cartoon answer is good enough,
When during psychoanalysis, when will we ever use the second law?
I can ask you a question that says, is this process in the combustor possible? Or, it's a little more explicit, right? Because you won't be just trying to find the characterization parameter, right? Because there you don't really have to, right? Right, but I could ask you, what's the entropy generation rate across component X, right? And then you would demonstrate your understanding of how to do the second law.
And in that case, would we just be given the heat transfer from the surroundings and like that extra information?
Potentially you can have to figure it out. Part C could be find the heat rejected from a condenser, and then part D could be, using that information determine the entropy generation rate. If it's something like that, I do always, when I'm grading, when I'm grading part E, I don't care what your answer to part D was. I'll just take that to be correct. And then, did you go through and do the process right? And that's the thing too. This is another big thing. If you get to the exam, even if you totally run out of time and you see a problem that says is this process possible? Even if you have no idea what to do, you see that and you write down, oh, I would do a second law analysis here. And if sigma dot was positive, then it's possible, right? Or if sigma dot was negative, then it's not possible, right? Or if you see something that says like, oh, what direction is the heat transfer? All you have to write down is like hip to win. And I'll be like, oh, that means you understood what that question was asking, right? Now, usually those kind of questions are only worth 1 or 2 points. But again, it breaks my heart a little bit when they're blank. So you can demonstrate sometimes your understanding without even having numbers, right?
All right, have a good weekend.
You too. Like I said, I will be available at 2 o'clock. So come see me then if you have more questions. Good luck, everybody.
Thank you.
Yep.
Have a good weekend.
You too. Bye-bye.
Thank you, Professor. I'll see you later.
Sounds good. Thanks.